Welcome back for module 2. We'll shift gears a little bit and move into a few different things. Today, we'll start off with a little bit of a review of some of the things we talked about before to try to put them into context. And one of the things that we've been talking a lot about is the autophotolysis of water. So if we have just water, nothing else, it will react through its AW equilibrium. It'll form hydrogen ion and hydroxide ion. And we know at this point that we could write that as two waters, right? And we have two waters reacting like a Bronsted-Lowry acid, and one water protonating the other, like hydronium ion, but I'm not going to go through that process. That's something we've talked a lot about. We know that if we are at 25 degrees, that we know that the Kw expression is the product of hydrogen ion times hydroxide ion, and it's just simply the products, right? A typical equilibrium problem. The products each raised to their product of the product each raised to their stoichiometric power divided by the product of the reactants each raised to their stoichiometric power. But in this case, water doesn't appear in equilibrium constant. So in this case, it simplifies to this expression. And as I was about to say a moment ago, at 25 degrees C, we know that that value is 1.0 times 10 to the minus 14. And I know when the book presented it the first time, they were like 1.01 times 10 to the minus 14, but it's pretty much universal that everyone just says at 25 degrees, 1 times 10 to the minus 14. We also know that we have an expression for pH, and pH is equal to the negative log of the hydrogen ion concentration. And recall that we ignore activity. So we don't worry about activity coefficients, and we don't worry about activity in this class. And when it comes up in the textbook, you're always going to ignore that if it's part of a homework problem or whatever. We're not going to calculate activity coefficients. Now, this whole pH is equal to negative log of the hydrogen ion concentration. That hidden in there is a notation that you'll actually use a lot in chemistry, and that's that typically we'll say we have Px, whatever x is, some unknown, Px, right? So Px, generally, if we say something like Px, we know that Px is equal to the negative log of x. So it's just kind of a notation that we use. And so with the Ka expression, oh, I'm sorry, let's call it the Kw expression. I misspoke. Kw expression. Let's take the log of both sides, and then, so I'll just rewrite it down here as log of Kw is equal to the log of H plus the log of OH minus. And then if we multiply both sides by -1, then we get negative log of Kw is equal to the negative log of H plus the negative log of OH minus. And so then we can go in and substitute what we know. This is the negative log of 1 times 10 to the minus 14. And negative log of H plus is simply pH. And negative log of OH minus is POH. So now this simplifies to 14 is equal to pH plus POH. And that is a very useful expression. And it holds as long as we're at 25 degrees C. I also want you to recall weak acid equilibrium. Weak acids only, let's say, I'll just say here, they only partially ionize. And we've used the generic weak acid HA, the generic weak acid. We can write it, and in this case, let's do it like a Bronsted-Lowry acid. And so the weak acid is going to protonate the water. Remember that water can act as an acid or a base. Bronsted-Lowry or Bronsted-Lowry acid, Bronsted-Lowry base. So in this case, we're going to have the weak acid is going to protonate the water. We get H3O plus A minus. And we can write the expression for Ka is H3O plus times A minus over HA. That is equal to some number, right, that we look up in appendix G. It's typically small. Typically a small number times 10 to the minus something or another, right? Because these weak acids only partially ionize. Now, I left off my brackets down in the denominator there. So in this case, right, again, you still don't see water in the denominator, but you do see that unionized weak acid, right? So unlike when we talked about strong acids, when they ionize, where we say the strong acid, the Ka is infinite, that's not the case for these weak acids, right? Typically, only partially ionized, and typically a smaller amount than you might imagine, right? So as we go on through this section, you'll start to get a feel for what is the magnitude of Ka values. And when we get on to talking about the Kb values, you'll find that the Kb values are typically smaller than the Ka values. So also recall weak base equilibrium. We wrote it before. Well, I'll remind you that weak bases only partially ionize. Before we wrote it as B plus H2O will undergo its KB reaction. In this case, water is going to act like a Bronsted-Lowry acid. It's going to protonate that Bronsted-Lowry weak base. So we're going to end up with HB plus. We took an H plus off the water, stuck it on the neutral B. Now we get HB plus, and then we're left with OH minus. We can also write the expression for KB, just as we've done before. And that is also equal to some number that is not in Appendix G. Remember, we talked about how KAs are often cataloged and put into tables and appendix in the back of the book or table within the text. You can look them up in the CRC handbook. Anybody know what CRC stands for? You hear it all the time, right? CRC. You guys know? Anybody know? You know? Chemical Rubber Company. They're the ones that started the CRC handbook. A little bit of trivia. Could be important something. So we've got these Ka values, they're cataloged. We don't have the Kb values. And you might recall in module 1, we derived a relationship between Ka and Kb, which we're going to revisit today. And if you know the Ka, you can calculate the Kb for any conjugate acid base pair. Okay? So you typically don't look them up, right? You typically calculate them. And Kb values are typically small, 2, and they're even smaller than Ka values. Now that's not what I'm talking about, is the general rule. So generally the Ka will be a little bit larger than the corresponding Kb, right? So they're typically, Kb values are typically a little smaller. Now, I do want to remind you that we could, we don't have to, but we could write the Kb equilibrium as A minus, right, plus water going through its Kb equilibrium. Same thing happens. You get water, right, protonating the A minus to give us HA plus OH minus. And we'll end up doing that a lot in this module, where we'll use the conjugate base form, right? So sometimes the book uses this B notation, right? You'll see it come up again and again. And sometimes we can just use the A minus HA notation, but it's the same reaction. The same thing is happening, right? B is acting as a weak base, water protonates it, right? And A minus is acting as a weak base and water protonates it. It's the same thing. So what's that? NH3. What's it? We got a name? Ammonia. Is it a strong acid or strong base? All of a sudden, everyone starts looking down, checking on things. So here's a point I'm trying to make. Okay, I can't stress it enough. It's absolutely imperative that you not have to think about these things. Some of this stuff, it's just, if you were over in French class and they said to you, merci beaucoup, right? That's the extent of my French, and it's not even, right? You wouldn't think twice about it. You got to be able to respond. And I really want to drive this home that, like, you've got to memorize those strong acids and bases. If they're just committed to your memory without any hesitation whatsoever, then you would know this is what? It's a weak base, right? It's probably one of the most common weak bases that you'll run across. What's it going to do? We put it in water. And it's a weak base. It's going to react through its Kb equilibrium. Water is going to protonate it, right? And then we get NH4 plus OH minus. So now, if you go back and you think about the original, when I talked to you about a few days ago, a couple of weeks ago maybe, I talked about the Arrhenius theory of acids and bases, right? And I talked about the Bronsted-Lowry theory of acids and bases, right? So if you think about it, the Bronsted-Lowry theory could explain why ammonia is a weak base, right? But the Arrhenius theory couldn't. If you look at the formula for NH3, it doesn't have some hydroxide ion that it can give up, right? If you look at it, go, oh, there's not even oxygen in the thing, right? So the way that ammonia actually fits the definition of an Arrhenius acid or base, it's a base, right, is that it has to go through the whole Bronsted-Lowry concept of being able to generate that OH minus over there because water protonates it, okay? So ammonia was one of the places where the Bronsted-Lowry theory could explain why ammonia is a weak base. And it's not immediately obvious with the Arrhenius theory of acids and bases why ammonia is a base. I just want to, again, trying to bring to the forefront of your brain some of the things we've been talking about for the last couple of weeks. And remember that I told you that this ammonia is, it's not ammonia-like, it's ammonia, right? But it's the ammonia-like nitrogen, right? It's got three things around it. So that's always going to be a base. So if you look at these amines, if they've got three things around them, right, they're going to be an ammonia-like nitrogen. But over here, this is ammonium ion. And it's got four things around it. And anytime the nitrogen has four constituents around it, right, it's an ammonium-like nitrogen. Okay. And I'm going out of my way, right? I'm enunciating ammonia, right? And ammonium ion. And it's annoying. I know it's annoying, but I'm clear. You don't have any doubts whether I'm talking about an ammonia type nitrogen or an ammonium ion type nitrogen. And later on, you may be standing up in front of a bunch of people talking about chemistry, and you need to be as annoying as I am. You need to be as clear as I am when I'm distinguishing between those two things. Or if I'm talking about other polyatomic ions like chloride ion and chlorite ion and chlorate ion, I purposely enunciate so that there's no doubt that the people listening to me know the species I'm talking about. It's really important, unless you don't know what you're talking about, and then you're just trying to, right? Sometimes you're just trying to get through it. But that should be the exception, not the rule. So the rule is to train yourself as a chemist so you can start talking in the language of a chemist and you can do it clearly. So remember this whole thing about the ammonia and ammonium ion, like nitrogens, and try to make that part of your repertoire. What's that? Wow, Dr. Emmert, that's H2SO4. So we do that a lot, don't we? Like I could write BrO3 minus up there. Oh, that's BrO3 minus. It's not, right? BrO3 minus is bromate ion. What's H2SO4? Were you asked to memorize it at some point or another? You were, right? Yeah. It's a strong acid, isn't it? And so it's a strong acid, so we can write a Bronsted-Lowry type reaction here where the H2SO4 is going to protonate the water and we get HSO4 minus plus H3O plus. And that's Ka1, right? That's the first one. And what do we know about Ka1? It's infinite, right? That first one is strong. Everybody agree with that? Well, this, what's that? Well, that's HSO4, Dr. Emmert. Nice. So hydrogen sulfate monobasic, that's one way to name that, right? Hydrogen sulfate monobasic. Doesn't look like sulfate, does it? Sulfate ion is SO4 2 minus, but right, you can kind of see that that's a sulfate ion in the making as soon as they can get rid of that H plus. Right? So we can take that and we can write HSO4 minus, and we can have it react with water through its Ka2 equilibrium, and we end up forming SO4 2 minus and H3O plus, and Ka2 is equal to some number in index G. Did you know it does? It's still a fairly strong acid, but it's not strong, right? It's weak, okay? I mean, it's still, as far as acids go, HSO4 minus, it never is strong, right? It's always weak. I probably misspoke a little when I said that. But compared to a lot of other weak acids, like acetic acid, for example, it is a stronger acid than acetic acid. Remember, we can look at those Ka values, right? Or we could look at pKa values, right? We'll talk more about that. So just remember that Ka1 is strong, right? Ka2 is weak. Not for every acid, but for H2SO4. So it's kind of an anomaly. First one's strong, second one's weak. Draw a line. Draw a line there. So it's like little concepts. No line touch it. We're going to another concept. What's that? Is it on that list of strong acids? No. In fact, there was only one of those strong acids that was not a monoprotic acid, right? That was sulfuric acid, and we talked about the exception just now. So if you see, right, a polyprotic acid, a diprotic that's not sulfuric, or triprotic, or tetraprotic, or pentaprotic, or hexaprotic, you know almost immediately, don't you, that it's not one of those strong acids, right? I'm just making you aware of that if you haven't thought about that, you haven't caught that. So H3PO4 is a weak acid. We can very quickly, we can go, oh, H3PO4 will react with water through its K1. I'm going to drop the A designation. Remember we talked about that before. Typically, if you start to get a lot of people typically drop the A. You just recognize that's a Ka reaction. I'll call it K1 because it's the first proton. And that phosphoric acid is going to, if I take an H plus away from it, right, I'm left with H2PO4 minus, and that H plus is going to go over to that water. But now, this H2PO4, what do we call that? Hydrogen phosphate monobasic. Right, that's a good way to refer to it. So this over here, hydrogen phosphate monobasic, right? Something I'll add here. Notice this is something that the book will kind of start to do, but I will do forevermore. Okay, I will write acidic protons out front. See how I have the 3 acidic protons and I've written them out front, H3PO4. And over here, there's still 2 more acidic protons. So we can have H2PO4 minus can also react with water through this we would call the K2 equilibrium. Take an H plus off, we're left with HPO4 2 minus hydrogen phosphate dibasic, and we formed another molecule of hydronium ion. But now that hydrogen phosphate dibasic still has an acidic proton out front, so I can write it down here, and it can react with water through its K3 equilibrium. And we take an H plus off, so what are we left with? PO4 3 minus phosphate ion, and we form another molecule of hydronium ion. Now, can that phosphate ion react further as a Ka reaction? It's out of gas, isn't it? And then it's got no more protons, no more acidic protons to give up. So in terms of writing its Ka equilibrium, right, it's done for. So remember that loss of first proton is K1. Loss of the second proton is K2, and loss of the third proton is K3. K1 will always refer to the species that has the most acidic proton. That's another way of thinking about it, right? So K1 is going to refer to the ionization of that species with the most protons, in this case, H3PO4, right? If we had a tetraprotic acid, K1, you have H4A as an example, right? Some generic tetraprotic acid. Then Ka1 will still, we would refer to the H4, the first proton is given off that species. Let's take this phosphate ion. Now, what is phosphate ion? Is it have the possibility of being a weak? It's not, we know it's not an acid, right? There's no acidic protons out front. We just went through where we went through the equilibrium for phosphoric acid. And so this is the conjugate base of hydrogen phosphate dibasic, right? Remember, if we go back, when we look at this hydrogen phosphate dibasic, right, is bronzoluric acid. And when it reacted, it produced its conjugate base, phosphate ion. So when we write phosphate ion here, this is the conjugate base of hydrogen phosphate dibasic. So it can react with water through its Kv equilibrium. And then the water protonates it, so we get HPO4 2 minus plus OH minus. Now, this one can also accept a proton, so we can write HPO4 2 minus reacting with water. Take an H plus off that water, we stick it over here, right? We get another hydrogen, so we get H2PO4. And since we stuck a plus on it, this -2 is going to go to -1, which I can just write as a minus. And so this is also a Kb. So this is Kb1 and this is Kb2. And we can actually stick another H plus on there. H2PO4 minus plus H2O. This will be Kb3, and we reform phosphoric acid and OH minus. So, reminder, kind of from the previous page, but also from previous lectures, I'll remind you that Ka1, I didn't write this down earlier, or K1 refers to the species with the most hydrogens. And remember that Kb1 refers to the species with the least number of hydrogens. So in this case, KB1 is referring to phosphate ion. It's given up all of its acidic protons. So now if we look at all of these, I know we can't see everything, right? So if we look at these reactions, right? And then we look at these reactions. Are they just the opposite of one another? Are they just the reverse? It's not. It's not the reverse, right? There's a little bit more to it than that. So let's take a look at that as a reminder. What is the relationship between Ka and Kb for a conjugate acid base pair? And you might remember we've talked about this before. Let's take the generic reaction for HA, and I'll just have it ionize in the simplified notation to go through its Ka1 reaction to form H plus A minus. And now let's take A minus. Let's have it react with water through its Kb1 reaction. I think in this case I could leave off of ones. Keep them or not. It's a monoprotic acid, so I shouldn't have put the superscript, the subscript one. So water's going to protonate the A minus, and we're going to get HA plus OH minus. So this is our Ka. This is our Kb reaction. We're going to add these two reactions together. And when we add these two reactions together, remember that species that are the same on both sides will cancel, and we'll be left with water undergoing its ionization on H plus OH minus. And so this is the Kw reaction. And when we add reactions together, we multiply equilibrium constants. And so Kw is equal to Ka times Kb. And this reaction is true for any conjugate acid base pair. So now, if you know the Ka, you know the Kw water, you can calculate Kb. So if you go to Appendix G, look up the Ka, you can calculate the Kb for the conjugate base of that weak acid. Just to point this out to you, earlier up here, we could have written the expression for Ka as being Ka is equal to H plus times A minus over HA, and AB is equal to HA times OH minus over A minus. So now if I multiply these two equilibrium expressions times one another, if I do that, then A minus cancels, HA cancels, and I'm left with H plus OH minus, which is equal to AW. So it works if you use the equilibrium expressions as well. You add the two reactions together, like we did up here earlier, add the two reactions together, we get the KW reaction. And when we multiply Ka times Kb, we're left with the KW expression. So either way you turn it, right, this Kw is equal to Ka times Kb for a conjugate acid-base pair. It's an important equation. It allows you to calculate Kb when you don't know the Kb, right? You have a Ka, you want to know the Kb for the conjugate base of that weak acid that you got the Ka for, you can now calculate it. So let's consider monoprotic weak acid base equilibrium. And let's compare formic acid and benzoic acid. Anybody know what formic acid is? Anybody ever been stung by a fire ant? Some guys got at least one person. Only one person? Other than me? Fire ants haven't got you? So you either have protective parents who warned you about them, or you don't get out very much. Because if you get out very much around here, you're gonna run into big fire ant hills. Why does it sting? Because they're injecting you with formic acid. That's why. That's one of the reasons. So we take formic acid, which the book writes this way, HZ double bond O, OH. It's the simplest of the carboxylic acids, right? But I'm going to write it this way, HC O2H. How's that? All right, and there's no reason that one hydrogen is smaller. I'll bulk it up a little bit. So now, this hydrogen here on the carboxylic acid group is our acidic proton. That's our acidic hydrogen, right? And this one is covalently bound to the carbon atom. Okay, so what I've done is I've taken this one, the acidic one, and I wrote it out front. And then I just condensed this formula so that we're not drawing this 2D structural formula. Because we don't have time to fool with all that. We've got other things we have to do, right? So I want you to get in the habit of not worrying about these organic style structures, right? We'll start doing them more this shorthand way, right? So from now on, we'll start to write these things more like this. Every now and then, occasionally we'll come upon an example, and I may at first draw it out structurally so you can understand where the acidic protons are if it's confusing. But for the most part, we're just going to start using this condensed nomenclature. Turns out, if we look it up in Appendix G, the Ka for formic acid is 1.80 times 10 to the minus 4. So what would be the pKa? Remember what P says? Little p out front of something says, whatever I'm out front of, take the negative log of it, right? So pKa would be the negative log of the Ka, which is negative log of 1.80 times 10 to the minus 4, which will be equal to, I'll write it down here, 3.744. Okay. So now we know something about the Ka, and we calculated the pKa of it, which we'll actually start to use more and more. I'm going to throw in a little aside before we go to the benzoic acid. Okay, so when you're looking at your textbook, some of you have version 10, some of you are working out of some older versions, 9, 8, so I think I told most of you I wouldn't go past 8, right? 8, 9, and 10 are pretty good. But here's the point I want to make to you. Okay, so some of you may actually be studying in groups sometime, 2 or 3 of you together. Okay, so there's something that may come up. It comes up, I think, a little bit later, more often than now, but I want to mention it now. So I'll use you guys as examples, right? So you got 10, you got 9, you got 8 edition, right, of the textbook. Okay, when you go to look up a Ka in Appendix G, don't be surprised if there are sometimes little differences between the 3 editions. So it comes up a little bit later in some of the other stuff we're going to be doing in Module 3, but it may come up now. So here's the deal. If you're working the problem in 10 and you want to get the answer they have in the back of the book at 10, right? Use the Ka or the pKa they've given you in 10. And if it's a little bit different, if the 3 of you are working together and you find yourself, oh, I got the answer that's in my book, but it's not, you might see that sometimes these Ka values might change a little bit from edition to edition of the text. Or if you Google it and look it up online, and pull some Ka offline. It might differ by a little bit. They're practically the same, but don't let that trip you up. So always when you're working homework problems, stay consistent to your textbook. Don't pick the Ka from somebody else's different edition of the textbook. Try to work the problem, then look the answer up in the back. It might be a little off. Okay, so it's just something that I've seen come up, and I wanted to make you aware of it. Okay, does that make sense to everybody, what I'm talking about? So just try to stay consistent with your textbook, right? And you should be fine. But if you ever find yourself getting kind of the same answer, but not the same, that's the first place to look. See if you pulled out two different KAs trying to solve the problem from two different textbooks, right? Sometimes it happens. Benzoic acid. But you had to draw that one in organic chemistry quite a bit. How's that? Some of you may have, sometimes you put a circle in to show the aromaticity, sometimes the 3 double bonds, right? How might we write this? How many acidic protons does benzoic acid have? Just got one, doesn't it? Talking about monoprotics, it's just this proton out here on the end of that carboxylic acid group. So I might write this as H, right? And then, so each one of these is a carbon, right? With a hydrogen on it, right? So I got what? C6, right? And then, but these hydrogens that are out here on this benzyl ring, right? They're not acidic, so I don't want to write them out front, right? They're not acidic. So there's 1, 2, 3, 4, 5. So C6H5O2. Make sense? And you don't have to draw those rings and everything. We got everything we need to know. That acidic proton is out front. Now, if I take an H plus off of it, what do I have left over there? C6H5O2 minus. Because I took an H away, the acidic one, and I took a plus away from a neutral compound. So now we could write this as HC6H5O2 plus water. And then we would get C6H5O2 minus plus H3O plus. All right, so that's benzoic acid. I could have done a similar thing up here. Why don't I sneak it in here? All right, so we could have written HCO2 H plus water gives us CO2H minus plus H3O plus. Right? So we could have done that for the formic acid as well. Right? Just we wouldn't have had to draw that structural information we don't necessarily need. Now, to get back on point, the Ka for benzoic acid is 6.28 times 10 to the minus 5. And remember what we said for formic acid, it was 1.8 times 10 to the minus 4 is the Ka value. So which of those two is the strongest acid, formic or benzoic? Based on the information you have right now. The one that has the larger Ka value is the one that's going to produce more hydrogen ion in solution or hydronium ion in solution, right? Because the equilibrium lies further to the right on the larger number for Ka. So formic is a stronger weak acid than benzoic. Everybody agree? Is it ever strong, formic acid? We can say that it's stronger than benzoic acid, right? But it's always a weak acid, right? So if we look at two, right? We look at two species like that, two weak acids. One can be stronger than the other, but it will never be a strong acid. Never gets on the list, right? Never makes its way to the list that you memorize. If we take the pKa of this Ka, right? The pKa is, what's that? Yeah, it is. It's 4.202. So notice this. It's hard to get them both in there. I think I can get them both. Right. So notice that the stronger acid has the larger Ka, but the smaller pKa. Right? Weak is always conjugate to weak. That's kind of what I was saying earlier, but it's just an adage that I want you to kind of commit to memory. Weak is always conjugate to weak. A weak acid, when it reacts through its Ka equilibrium, will produce a conjugate base, right? And that conjugate base that gets produced is itself a weak acid. So a weak acid will produce a conjugate that is also weak, a weak base. Okay? If we have a weak base, ammonia, and ammonia reacts through its Kb equilibrium, it will produce a conjugate acid, ammonium ion, right? But ammonium ion will be a weak acid. And so you always, weak is always conjugate to weak, right? You always end up producing something. You never produce a strong acid or base from a weak acid or weak base. Never happens.
Will a strong acid make a conjugate strong base?
Test it out. Tell me what you find out. Think about it, but not now. Listen to me now. So this, like we said. So let's consider a weak acid. Generic weak acid HA. And HA has a Ka value from appendix G. It's not really in there because it's a generic weak acid. But it has a Ka value that is equal to 1 times 10 to the minus 4. The conjugate base would be A minus. And A minus has KB equal to KW over KA for HA. So if we put the numbers in, this would be 1 times 10 to the minus 14 divided by 1 times 10 to the minus 4, which is equal to 1 times 10 to the minus 10. There's no leeway with this. We're constrained, aren't we, by that whole, by the relationship between KA and KB that we talked about. Right? It can't just be anything. We're constrained by that equation. Okay? And so if we have a generic weak acid that has a Ka of 1 times 10 to the minus 4, just like we have here, the conjugate, the Kb for the conjugate base, A minus, can't just be anything. It's fixed at what it could be by that Kw is equal to Ka times Kb for a conjugate acid-base pair. You see, so it can't be anything else. It has to be 1 times 10 to the minus 10. And both of those values, right? The Ka is a small number, and the Kb that we calculate from it for the conjugate base is a small number. So weak has been conjugate to weak. And you'll notice that what I pointed out earlier, right, is that you'll notice that that Kb value tends to be smaller than the Ka value. Now, let's consider another one. Consider weak acid HA with Ka equal to 1 times 10 to the minus, I'm gonna draw a line through that, with Ka equal 1 times 10 to the minus 5. So just ignore that. Okay? So now we got a different one. Yeah, it's still HA, but it's a different one. It's a different weak acid. And it's so different, it's got a different Ka value. So order of magnitude less weak than that other one, or order of magnitude weaker, I should say, than the one we just talked about. And so if we have a weak acid HA with a Ka of 1 times 10 to the minus 5th, right, then Kb is equal to Kw over Ka, where Ka is the Ka for that generic weak acid. We plug the numbers in, 1 times 10 to the minus 14 over 1 times 10 to the minus 5. And so what does Kb turn out to be? 1 times 10 to the minus 9, right? So in this case, we're back in the same boat again, right? Can't just be anything. It's constrained by that equation. But do we notice a trend? So what happened when Ka was stronger, right? This generic one is stronger than this generic one, right? This Ka is larger than this. They're both weak, but between the two, the one with a Ka of 1 times 10 to the minus 4 is stronger than the one with a Ka of 1 times 10 to the minus 5. But what happened when we calculated the KB? The KB for the stronger acid was 1 times 10 to the minus 10. What happened to the KB for the weaker of the two acids? It's 1 times 10 to the minus 9. So which is stronger? Which is a stronger weak base? The one in the first example or the one in the second example? What's that? The second one, right? Okay. So let's take a look at something else. Let's go ahead and it's in your book. So notice the trend when HA, so when we have, let's say when we have a conjugate acid base pair, HA and A minus, when Ka is 10 to the minus 4, and then notice that Kb was 10 to the minus 10. And in that second example, if we look at that conjugate acid base pair, HA and A minus, I said that Ka was 10 to the minus 5th. And when we calculated Kb, it was 10 to the minus 9. Now let's consider another one, another pair, HA over A minus. Again, generic, but this time Ka is 10 to the minus 6. Then Kb is going to, if you go through the same thing we did earlier, right? Kb is going to be 10 to the minus 8. You can prove that to yourself. So what do we see happening? As when we look at these Ka values, as we're going down here, what's happening to those HA values for Ka? They're becoming smaller, aren't they? Thus weaker. But the conjugate base that's forming is actually getting to be stronger. So as HA becomes weaker, A minus becomes stronger. But never strong. Never gets on the list. Right? Never gets on the list. It's always going to be weak. In this module, you'll be asked to solve the typical weak acid problem. What is that? Something like find the pH of a solution of some weak acid, HA, given the formal concentration of HA and the Ka or pKa. How do we go about solving that problem? We need a plan. So let's touch upon a few things first. I don't know if it's a few terms, but we'll just say, let's clarify a term. And that term is formal concentration. What is it? Well, it's an older term. You see it a lot in older textbooks. Our textbook uses it, but it's kind of a holdover from the past. It's something that we've actually dealt with before. Okay, so let's consider we have a weak acid, HA, reacting through its Ka equilibrium to form H plus A minus. And before, we would write a mass balance equation. So the mass balance would be equal to, and we don't know how much we start out with, but we know if we put HA into this water, we're going to have HA and we're going to have A minus. So whatever that number would be, which we're going to call the formal concentration F. And I know that we called the response factor F earlier when we were doing calibration work. Remember that? But this is different, right? Now we're going to use F to be formal concentration. And so that formal concentration is going to be equal to all of the HA plus all of the A minus. And that's all formal concentration is. It's just another way of stating the mass balance expression. Another way to describe the mass balance expression. That's all. So let's go back to a generic weak acid problem. So we've got some generic weak acid, right? And so we could write the expression for the mass balance equation using the formal notation. So we write F is equal to HA plus A minus, just like I did on the previous page. we can write the charge balance equation. The charge balance equation would be all the things with a positive written on the left-hand side, right? So if we've got this generic weak acid, what do we know is in solution? We got, it's water, right? It's an aqueous solution. So we know we got H plus, we know we got OH minus. Got anything else that's positively charged? Not, right? Think of that weak acid equilibrium. Do we have anything else then? So there's nothing else that's positively charged for weak acid, HA. What about the negative species? No, we got OH minus. We got anything else? We got A minus, don't we? So if we write the charge balance for this system, there's our charge balance equation. What about our equilibrium? Well, we can write that equation, right? We got, let me ask you, what are the two things that are going on? You got the weak acid, right? So you have weak acid, HA, reacting with water to form A minus and H3O plus. That's the Ka. Any other reaction going on in aqueous solution?
Water.
There's one more.
Water.
It always is occurring, right? The autoionization of water. I'll write it this way, AW, and we end up getting a proton transfers over to one of the waters. We're left with H3O plus OH minus, right? I wrote it a different way. I wrote two waters just to keep it consistent with the hydronium ion that I'd written in the equilibrium reaction. And so we also know that we have a Ka is equal to A minus H3O plus over HA. And then we have KW, which is H plus OH minus. So now we're going to collect all the information and what we end up with four equations and four unknowns. This leads to a cubic expression, not a quadratic. To solve a cubic expression, we need to solve simultaneous equations. And they can do that over in the math department really well. Some of you can probably do that really well. But we can also make simplifying assumptions based on our chemical knowledge. And reduce the cubic expression to a quadratic expression. We will do this. Next time. Stop there for today. We'll pick up on Wednesday and we'll look at these simplifying assumptions that we can make so that we can solve, set up and solve a weak acid problem, place it in the context of a quadratic, and then follow along with some of the things that we've already done.